Thank you for attending my talk, and it's been a great honor for me to join this series of talk. So what I'd like to share today is our work recently on the modeling and experimental investigation of the finger-screen interaction, specifically under the surface haptic context. So what is haptics? Haptics is this technology that stimulates the sense of touch and motion, especially to reproduce something remotely or through simulation that you're actually interacting with a physical object that's not there. So the haptic technology is really crucial for the next generation of the human-machine interactions, and it's been identified thus by different agencies like the NAE Grand Challenges for the 21st Century. They said that, okay, enhanced virtual reality is going to be one of the great challenges. And also the EASF 10 Big Ideas marked the future work at the human technology frontier. It also got to do with the human and machine interaction. Under this big context, we have different varieties of haptic devices being introduced into the world that we didn't expect that would actually come there. So, for example, in June of 2019, Canvas, this company, released the first commercial touchscreen with the integrated haptic surfaces. So what it does is that when you touch its surface, instead of just feeling like a flat, smooth surface, it's going to display the texture on the surface. So you can feel somewhere to be rough, you can feel somewhere to be smooth based on what you are touching as they define under the screen. So haptics is really a growing market, and it's been growing for a long time. Projected in the 2023 is going to reach the market size of about $22 billion US. So because it's got really a lot of application scenarios where haptics can be pretty interesting, like mobile phones, tablets, anything that's got a screen, cars, and also it's got everything to do with wearable electronics, virtual reality, and healthcare. Specifically to our surface haptic technology, its effects are basically driven by friction and vibration. And what we're talking here today is the interaction or the interface between a finger and the electroadhesion surface, where when you apply an electrostatic field, your finger feels the changing friction force. So why do we care? Because the effect is there, but when we're dealing with a high volume of consumer electronics, it's always highly desirable to maximize its performance, reliability, battery life, and reduce the cost, everything that's got to do with money. And however, this technology at its current point is sensitive to a lot of variations that we do not like. For example, environment. The same device won't perform equally well in, say, Houston, where it's really humid, or Minnesota, where it's really dry. And there is also this user difference. Age group, gender, and user preference also play a role. And say someone that's sweating a little bit more may feel the performance of this device not as good as someone that has a drier skin. So there is actually a large potential for researchers of different backgrounds to really impact the performance and reliability of this new technology. As we are looking at the interaction between the finger and the screen, we ask ourselves, so what are the factors that we have to consider within this context? So it's actually turned out to be pretty complicated. Got a lot of factors in this seemingly simple interface. Like we have the finger topography and the glass texture, and then we have the capillary forming in between them due to sweat, condensed water, lipid, and sebum. And we also have the electrostatic field that's applied there to enable the electrical adhesion of this device. And the electrostatic field will affect the material property, and vice versa. The material property will affect the electrical adhesion forces. So it's got a lot of things going on at the same time, and we really want to develop a good understanding of this interface. When we're talking about the design principles of this device, we want to increase the nominal electrical adhesion effect. And to do that, we want to, say, decrease the sensitivity to variables. As we said, we have a large group of users. So to do that, we have humidity as a change in variable, and we have sweat rate from different users, and we have different finger properties. And well, the funny question is, all these things are directly related to capillary, and it seems that capillary is affecting it. So it is really decreasing the capillary effect the way that we want to go. This question will be answered in the later part of our talk. So for screens, and we also want the surface modification to be invisible because it's a screen. And if you make large asperities of the size of, say, millimeters, you will definitely see those, and it's not going to help at all to your performance of devices. So it has to be nano-textured and below the wavelengths of light, so it's not visible. As we say here, there is this need to develop a model to understand the physics in the touch interface. What are the relevant mechanisms that's governing the friction and adhesion between finger and contacting surfaces? And how do we really model them because they're all together? And then how do we predict the sense of touch on the surface with different textures? As we delve into this topic, we said, okay, we have to do the experiment first. So this is the experimental setup that we designed and developed. So it's a tribometer, and this little movie shows you that how it basically works. You put your hand in there, fasten it against the tribometer, and then the screen, testing screens are fixed on top of a moving stage. What makes our tribometer a little bit different from the others is that we actually introduce a control circuit that controls its normal force, because really we're dealing with the friction force and we want to have an accurate measurement of it. And we all know that friction force is very sensitive to the normal force they apply to it. And that we're dealing with the finger, so no one can hold their finger very, very still. So what you have to do is you have to compensate for the finger movement. And what we did was introducing this adjusting stage to maintain a constant normal force. And this stage actually works pretty well. As you can see that the orange curve on this graph here is even a trained test subject where she put her finger in this tribometer and tried her best to maintain a normal force as the stage travels laterally. And as you can see that this lateral force still goes, this normal force still goes all over the place. Whereas once this control algorithm is turned on, it's maintained at a much better position of the normal force. So with this test stage, we are able to gather some friction force in our experiments. For example, the figure on the bottom left is a very typical curve that we get in an experiment. And as you can see that the friction force grows gradually until it gets into a steady state. And we always use the steady state at the end part of the curve because it's got a much more steadier and reliable result to be compared with the others. And this is actually one thing about doing experiments with real human fingers, that you can't expect as good performance of the data as you have with the, say, something that just stays over there. And here, this our experimental result. So we did this experiment on 3 types of glass textures, as you can see on the right side. And they are the similar shape, but gets a little bit deeper from sample 1 to sample 3. And then we applied the normal force, and we apply different relative humidity and apply the electrical adhesion voltages. As you can see on the curves from the left, we see all the friction force goes up with relative humidity. So that's one check that we do see that the friction force change with environmental humidity, and it goes and it also goes up with different textures. For example, the red one, which is the most shallow texture, has seems to be affected a little bit more than the blue one, which is the tallest texture. So that tells us something, that this texture is affecting how the humidity is affecting it. And we know that humidity affects the behavior by changing the material property and different formation of a capillary. So capillary is doing a lot of things in here, and why is it affecting one more than the other? Then if it's all attributed to the material property change, then it really doesn't help explain why it's affecting one texture more than the other. And then we say, okay, it's probably more got something to do with the capillary. And also, as you can see, is when you apply the electrostatic field in between the finger and the surface, you see an increase in the friction force clearly from the experimental results. And this increase in the friction force is also different at different textures. As we did this relative increase of the friction force, it's plotted on the right, is that you see the texture that's got the shallowest texture has the largest increase of friction force, but it also peaks at around 50%, 55% of relative humidity instead of the tallest texture that maximized at really the highest humidity level that we got, which is 75%. So as has been argued, is that perception has been sometimes shown to be related to the delta F over F, which is the change of friction force over the friction force itself. So we also calculate this parameter, and as you can see is that again, this texture that's got the shallowest texture has a larger effect. And this is more or less consistent with the participants' experience as she felt this change in friction force, was that the perception reduces at 75% relative humidity, and she felt the maximum force at 55%. And then we say that the increased texture does reduce the variability of the actual adhesion effect. So what is the reason for this electrical adhesion effect? And why is it sensitive to the change of the electrostatic field? As we were thinking, there are several contributions, but what we want to emphasize here is the electrowetting effect. As you can see here, we did record some videos of the droplets changing its shape when we apply a voltage between the drop and the surface of the glass. What is interesting that is on the left side of this this far left video, you're looking at a droplet of DI water on a very clean wafer, and we're gradually increasing the voltage from 0 volt to 500 volt. You can see that the contact angle is decreasing, but we can say the decrease is limited. What happens with salt water, which got a lot more ions and should help a little bit to of interaction? And you see, all of a sudden, even when we only applied 100 volts, it's already decreasing to a contact angle even smaller than what we have with the deionized water at 500 volts. Now, for the real skin that we're dealing with, on a glass surface, is that our skin is producing sebum, oil, and lipid all the time. And what if we are really like contaminating our glass sample a lot, and then there are residues of these sort of oils on the surface? And so we did a rough surface that we just contaminated the surface a lot, and then measured the contact angle. And even after applying 150 volt, the contact angle changes hugely, even a lot more than the saltwater case. So we say that, okay, the contact angle change is definitely there. And because the contact angle is changing, we have to say that the capillary is changing. And what affects the capillary force? Contact angle. Different contact angle results in totally different capillary force. And now that we are seeing a lot of this contact angle change, we really have to consider this phenomenon of electrical wetting in our model. So what we did in our model is that we did this multi-capillary model where we consider the texture of the glass, textures of the finger, the surface energy of the capillary, and amount of water that's in the interface. So this modeling process goes in 4 steps. First, we have to gather the texture of the glass, the texture of the skin, and then we calculate the deformation with the finite element method, and we simulate the water distribution from the minimum surface energy assumption, and calculate the capillary force through circular approximation. The texture of the finger is actually very, very interesting. We did this molding with the dental mold and extracted the texture of the finger, as you can see on the right-hand side. This 2 red regions corresponds to part of the groove, and the deep blue region are the ridge of one fingerprint ridge. And if we really zoom in onto the tiny little region of this ridge, you can see like this shape of a flake that's got a size of around 10 micrometers, and it's got very clear edges at its boundary, which we argue is very clear representation of one single corneal site, which our stratum corneum is formed. Our very top surface of our skin is formed by layers and layers and layers of the stratum corneal sites. And if we look at the center of these corneal sites, you see the texture of them. And it is this texture of these corneal sites that I'm modeling in my model, because they are forming the really building blocks of the interface between the finger and our different screens. So this is very standard. We do the deformation calculation in ANSYS with the contact algorithm, and we define a bunch of material properties based on what we can find. Stratum corneum cells are 100 megapascals of its Young's modulus, and soft tissues below it, we assume is to be 10 megapascal. Of course, here we are only simulating one layer of the stratum corneum cell, because it is this interaction between the cell and the interface and the glass that we're interested in. So this is the contact area simulation. As you can see, when it's pressed, when the finger surface on the top right corner of these 2 plots are in contact with the glass textures on the top left corner of these plots, contact area is only forming in limited regions in our plot. And these contact areas are marked by the little red dots. So what we conclude from these observations is that the contact areas are reflecting the intersection between the highest asperities on the finger and the highest asperities on these texture glass. But if the gradient of the feature on top of the glass is too shallow, for example, this case on the right, then we see that the contact area really distributes all over the place. It doesn't really care where it's contacting. Whereas when it's kind of sharp, the contact areas are more or less concentrating on the highest peaks. So this is for the contact simulation. As we said, the contact simulation gives us a profile of the contact interface. And based on that, we can move forward to the simulation of capillary. How do we simulate capillary? We know that capillary formation is governed by the surface energy. And there are equations describing it really well, this Young-Laplace equation. But to solve that, you have to really solve it numerically, and it really only works for a 2D case. And then for our application, we really want to know how the capillary interact with the 3D profile. So we say, okay, let's approach this capillary through this optimization approach, where we optimize the surface energy of these each little capillary bridges and find their minimum surface energy at the constraint of constant volume. So we try to compare our approach with the Kelvin's equation, directly solving the Kelvin's equation in a 2D scenario, and yes, they match perfectly. So we know, okay, at least the minimum surface energy approach works. So how do we then simulate the capillary distribution in the interface? What we assume is that in its initial form, we have a whole bunch of small droplets, more than enough. And then each of these droplets are free to move within the interface and find their own spot of the minimum surface energy. And then when these droplets find each other, they will merge. Or they can decide to reside only on the top surface or the bottom surface. So here is one example of our run simulation. The dark blue circles represents the capillary bridges that haven't been calculated yet. And the light blue circles represent those droplets that actually forms capillary bridges. Pink ones represent those droplets that are attached to the bottom surface only, and the green ones to the top surface. These two types of those droplets does not contribute to the capillary force. So this is what it looks like when we have only a limited amount of droplets in the interface, and it shows how the simulation runs. As you can see, each of the droplets is calculated and find its best position. And as you can see, some of the droplets here decided to reside only on the glass surface or only on the finger surface, depending on which state give its lowest minimum energy. So as we have developed this model, we say there are a bunch of factors that are affecting the performance of this model. For example, the finger model as we include here, a geometry that's really at the cell center of this corneal site. Or we can do this similar thing at the cell edge of the corneal site, where we find that really the larger gaps doesn't really give you much capillary bridges, so it's not contributing any capillary force in that case. And then we also tried the glass profiles, because the similar glass have, when looking at the 10 micrometer by 10 micrometer little window, it's going to look a little bit different. So we look at the profile on the different glass, and lucky enough, the curve produced by this model looks similar enough, because this is based on a Monte Carlo approach. So we're not expecting the curves to overlap on top of each other, but instead we evaluate how much error and deviation this Monte Carlo approach is giving us. So this is an example of our result with the varying total volume, water volume, and it's generating different capillary forces. As you can see, when the volume of water is really small, the capillary force is really small. And when you increase the water volume, this capillary force kind of plateaus. And other factors does affect this, like when you press your finger harder, which leads to a larger Z displacement, you see a larger capillary force. So with this model, we are actually able to compare the contribution of the electrical wetting to the contribution of the electrostatic to the friction. So what we do is that we're using this Bode-Haber's assumption that the friction force is linearly related to the real contact area. And the friction force here is expressed as tau, which is the shear strength, times the contact area, real contact area. So if we know how much contact area is contributed from the electrical wetting and how much contact area is contributed from electrostatic force, we can really compare the contribution of these two. So what we found was that, interesting enough, at this condition that we're looking at, this electrical wetting can contribute as much as 60% of electrical adhesion effect, as in the increase of contact area. It's even larger than the change of contact area when we're only considering electrostatic force. So this really tells us an answer to our previous question: do we really want to limit the capillary effect to maximize the electrical adhesion effect? Because now that we're seeing that electrical adhesion is affected greatly by the electrical wetting, so we have to say, okay, let's take a second thought and think what is the best approach here. So that brings me to the conclusion. And as we say, we did friction experiments, and we see the friction force between the finger is affected by the humidity and capillary force. And we see that the electrical adhesion effect is also affected by the humidity. And we see that the contact angle is showing a significant change when we're considering sweat and the sebum at the interface. So our model proved that the finger glass interface deformation and the capillary are contributing to this electrical adhesion effect, and that our model demonstrated electrical wetting can contribute as much as probably 60% of the electrical adhesion effect. I would like to thank my collaborators on this project, Dr. Cynthia Hipel, Xinyi Choi, and Pirawat, John Felt from Texas A&M, and our collaborators from Canvas and Northwestern University. Thank you.
Thank you, Yuan. So I would want to hear your opinion first. So do you want to use the electro wetting for the to increase the electrical adhesion force?
Maybe, yeah. We're thinking about different textures, and if we're successful enough to come up with textures that are stable over this range of humidity, then it is something that we have to consider, because as we see that it's really contributing a lot to electrical adhesion. And probably the textures, Dr. Tsinghua has a lot to say on that, because he's an expert on the reaction to omniphobic textures. So yes.
Jing, do you want to say something?
Yeah, since Yuan mentioned about the expertise I have for the capillarity and surface energy stuff, so I do have a question for how you bridge the electrical wetting and the static contact angle together with the adhesion force. Since you are breaking off a bridge of liquid, do you only consider the contact angle, or you consider the interfacial adhesions like contact angle hysteresis as well?
So for now, it's mainly contact angle, and we are considering the hysteresis and adhesion. Adhesion is modeled more or less differently, and we're thinking about using this, introducing this Leonard-Jones model into that part. And the contact angle change, we were using data from the experiments, and we were both also considering the Lippmann's equation on that, and whether the Lippmann's equation is good enough at the scale. And we've seen studies that shows that that argues that contact angle really doesn't really change at that small scale. But then we are also looking at results published based on molecular dynamics simulation that argues that it does change a little bit, probably not to the extent that's been predicted by Lippmann's equation, but there is some sort of change. So in the later part of our model, we are considering what is the best approach to determine what is the change of the contact angle. Probably we'll have to use the molecular dynamics, which I know is going to be challenging.
Yeah, it's a very complex system.
Yeah,
thank you.
Yep.
So Yuan, this finding is based on the hard substrate, right? Glass.
Yes, because this is the target of our simulation, is that it's something that we want for the electroadhesion devices. And the best application scenario for the electroadhesion devices is any kind of screen that you touch. So most of our screens that we touch nowadays are hard.
Have you considered about if the substrate is soft?
It's going to be quite different, yes. And one thing that I can think about right now is that the contact area is going to be much larger. And if the contact area is much larger, then probably contribution between these two factors will change, because now that it has got a larger contact area, probably the actual adhesion from the electrostatic is going to be more significant. But who knows? You have to really run the calculation and do the experiment and find out. But you're definitely right. It's going to be very different.
So what if you just use some liquid to immerse your surface first, right? If you always can keep the liquid there, so will that be good?
That's actually a good thought. Yes. If you have a way to keep the liquid over there, then definitely, yeah. But before we realize that, no one's going to like their phone screen to be wet.
Maybe it's not water, but another
Another kind of oil. Yeah, that'd be even more messy.
More messy, yeah.
Yes, but if we're able to find a kind of liquid that just stays over there, then definitely, yeah.
Yeah, when you maximize the electrowetting contribution in the electroadhesion, how much of the voltage can you drop? Can you deduce?
So in our experiment, we are running the voltage up to 200 volts between the finger and the screen. Then in the electrowetting, we are, because there is this dielectric layer between the electrode underneath the screen and the electrode that we poke into the droplet. So that's about the same amount of voltage drop over there.
So if the voltage is very low, the contribution of the electrowetting is eliminated?
Yes, but then the electrostatic is also gone.
I see.
Yeah, so both of them are affected by the same control that we put into the system. And so that's why they're intertwined together, and why we want really to design different textures to couple them.
I think if you use softer material, probably the electrostatic force can be kept. And at the same time, there's some possibility to eliminate the electrowetting.
Probably, yeah. That's something that we can definitely think about. One concern I may have is that our skin is already pretty soft. The Young's modulus I use for this straightened corneum is 100 megapascal, which is actually on the upper side of reported value. And they have even reported the smaller values than that, 10 megapascal, or even softer than that. But at the same time, our Young's modulus of the glass is 77 gigapascal. So it's like 3 orders magnitudes and more larger than our skin. So if we want to really achieve something much softer and significant, we have to design the surface to be probably 2 orders of magnitudes softer. But that's also an interesting thing to think about, is that people have been thinking about electroadhesion not only on the hard surfaces, but also on the softer surfaces like leathers and other textures as well. So maybe, yes, soft mechanics and softer materials will have a totally different and exciting setup that we don't have on this harder screens. It would be very interesting to look into that.
Thank you. Any other questions? No question. Thank you, Yuan.
Thank you, Vahong.